All right, we're back to talk about some topics that may have been alluded to last year, but we didn't actually discuss them by name, or at least I don't think we did. The first one of those, well, the first two of them are what are called Kirchhoff's laws. Kirchhoff was a scientist who specialized in circuits, and he developed some of our thinking about circuits. Kirchhoff came up with two rules, the junction rule and the loop rule. Loop rule. Okay, now I said it right. The junction rule and the loop rule that govern how circuits work. We'll start with the junction rule. That one's pretty straightforward, and actually we did talk about this last year. I just don't think we called it the junction rule. The junction rule says that the current going into a junction must equal the current coming out of a junction. Why is this the case? Because of something called conservation of charge. Conservation of charge is the idea that you cannot just create or destroy charge. The total amount, the net charge of the universe has been fixed and has always been fixed since the beginning of the universe. If you want to, you can't just create charge out of nowhere. There are ways to create things like electrons, but it's more involved, and it involves the creation of another type of particle as well. So we're not going to get into that. But anyways, the idea of conservation of charge means that in normal situations, you can't just create or destroy charge. All the charge going into a junction has to go out of the junction as well. It can't just disappear, or more just can't appear. Charges can't be created or destroyed. So let's look at some examples. I'm going to look at 3 different examples. Let's say that we have, okay, here's a junction. We have current flowing this way, and then it splits at this junction. Out here, we have a current of 0.5 amps. Down here, we have a current of 0.2 amps. We want to know what that is. Well, the current flowing into this junction has to be equal to the current flowing out. If we look at the arrows, we see that we have one branch, or one path into the junction. The junction is right here, and 2 paths, or 2 parts of the current, 2 wires coming out. 1 wire in, 2 wires out. The wire going in carries half an amp of current. One of the wires going out carries 0.2 amps. So this wire must be carrying the current to make up the difference. So if 0.5 amps is going in, and we only know about 0.2 amps going out, that means that there must be 0.3 amps coming out in this. That's the junction rule. Let's look at a couple more. Okay, so here we have 2 wires coming together. There's a junction, and then the current is flowing out this way. Let's say that we have 0.4 amps coming down. We have 0.5 amps coming this way. So the total coming in is 0.9. There's only 1 wire coming out, so this must be a current of 0.9 amps as well. One last example. Let's do something like this. We have current coming in, out, out. And we could really, it doesn't really matter. We could have current coming in on 3 branches and out on 1. We could have current coming in on 1 branch and out on 3. It really doesn't matter. We could switch up the arrows. It really doesn't. Well, the numbers will change, but we could have any situation that we want. Let's say that we have 3 amps coming in this way, 4 amps coming in this way, and 6 amps going out this way. Well, the total amount of current flowing into the junction right here is 3 plus 4, which is 7. 6 amps is flowing out. That means that 1 amp must be left over to flow out this way. Okay, that's the junction rule. Very straightforward. A little more complex is what's called the loop rule. The loop rule says that when you are tracing around an entire circuit I'm going to change the wording on that. When tracing around a completed path, or a complete path in a circuit, you must start and end at the same voltage. Why must this happen? Conservation of energy. Remember, we deal with voltage because we don't want to necessarily talk about energy, actually. We talk about energy per charge. Once you have a circuit set up, at any point in that circuit, you should know what the voltage level is. What we're really concerned with is the voltage differences as we go across a resistor or across a lamp or across a battery. But if you set a certain voltage level at a certain point, then if you trace your finger all the way around that circuit, you should come back and be at the same voltage level. In other words, the voltage gains and voltage losses from that you go over as you trace around the circuit should cancel out, and you should end up at the same energy, the same voltage level. And that has to do with the conservation of energy. I guess I'll say this. Once you define a voltage level for a point on a circuit, once you define a voltage level for a point on a circuit, then that is, I guess I'd say, set in stone. No other value for voltage is correct for that point. Let me illustrate a little bit about what I mean here. I'm going to draw in a circuit. We're going to have, okay, so it's going to be a pretty basic circuit. So there's one resistor, there's a second resistor, and there's a lamp or a light bulb. And we're going to have voltmeters on all of these. So we can talk about the voltage drops and gains. Okay, and we're going to say that this is a 12-volt battery. So what I mean by the loop rule is if I say, okay, I'm going to make this determination, it's kind of like setting a 0 point that we've done. It's kind of like setting a 0 point like we did for gravitational potential energy. I want to say at this point right here, let's say that this is just when the current has gotten through the battery and the charges are right here. They haven't used up any of their voltage yet. Let's say that this is at 12 volts right here. Now, let's say that our voltmeters read this: 4 volts, 2 volts, 6 volts. What that means is that the voltage level right here is 12 volts. And it's 12 volts throughout this until we get past this resistor. The voltage doesn't drop, again, unless there's something with resistance. Let's pretend that these wires have no resistance to them. The voltage level is going to be 12 volts until we go across this resistor. We see that there's a difference, a potential difference, a voltage difference of 4 volts. So once we get to the other side of this resistor, we now have 8 volts. And we have 8 volts, 8 volts, 8 volts, 8 volts, 8 volts. Once we get to the other side of this resistor, there's a potential difference of 2 volts. Now we're at 6 volts. 6, 6, 6, 6, 6. We get to the other side of this lamp, that has a potential difference of 6 volts across it. Now we're at 0, 0, 0, 0, 0, 0. We get to the battery, we go through the battery the correct way, we gain 12 volts, we get back here, and we're still at 12 volts. Now, and that again, we've kind of talked about that before, but we've never called it the loop rule, I don't think. Now, what if one of these had been different? What if this had been 4, 3, and 6? Like you had done the analysis wrong and you had predicted this was going to be a 3-volt drop and everything else was the same. Well, then you would get back here and you would see that now there's only 11 volts. There's a voltage level of only 11. And what that would say is if you go all the way through the circuit, remember the circuit is just supposed to be bringing energy from one spot to the next. If you go all the way through the circuit and you end up with a different voltage level, you're essentially saying, well, we started off at a voltage level of 12, now we're back here at a voltage level of 11. That doesn't make any sense. There can't be 2 different voltage levels. There can't be 2 different amounts of energy per charge at a location. That means you've screwed something up, okay? The whole point of a circuit is even though these resistors and the lamps are dissipating energy, they're giving it off, the battery is supplying the same amount of energy the battery is supplying enough energy so that the amount of energy that's flowing through the circuit at any one point is the same. The amount being dissipated by the resistors in the lamp is the same as the amount of energy coming out of the battery. So we shouldn't be getting, as long as the battery is not running out of charge, we shouldn't be getting different voltage levels. That's the loop rule. If you were to trace all the way around, you should, and kind of go over the voltage drops and the voltage gains, you should end up back at the same voltage level that you started at. Okay, that's the idea behind the loop rule. And it sounds kind of it sounds kind of weird when you think about it that way. It also sounds kind of basic in some ways, but it's a very, very useful rule. It can really help when you're checking to make sure your circuits are correct. Before we finish this video, I do want to talk very briefly about switches and burnouts. We talked very briefly about switches last year. There might have been 1 or 2 homework problems on them. What a switch does, switches allow parts of circuits to activate or deactivate if they're open or closed. And the reason I want to talk about burnouts is because a light bulb burning out kind of functions like a switch. Light bulbs that burn out are like open switches. Okay? A burned out light bulb means that current can't flow through it. So again, let me draw a couple of examples for you. Here's a battery. Here's a resistor. And we're going to make another branch that has an open switch in it. There we go. Okay? So currently, little joke, this circuit is a simple 1 resistor series circuit. You might say, but wait, there's very clearly a branch here. Well, current can't flow through that branch because there's an open switch. So it's almost like that branch doesn't exist. It's almost like there is an infinite resistance right here, so no current is going to flow around this way. The second resistor, and that's actually how you should treat open switches. Treat them like a resistor with an infinite resistance, okay? Current doesn't like to flow through infinite resistance. Matter of fact, it can't flow through infinite resistances. The second resistor has no current flowing through it because the switch is open. And like I said, that's kind of like infinite resistance. Now, what happens if I close that switch? Now, with a switch that's closed, the second resistor comes into the circuit. And let's do a little bit of analysis. When we go from one resistor to two resistors in parallel, you might say, oh, well, that probably means the resistance goes up. But remember what the equation is for equivalent resistance in a parallel circuit. If we increase, or if we put another resistor in, that's going to make the right side increase, right? We're adding another fraction. Even though it's a fraction, even though it's small, we're increasing the right-hand side. However, in order to find the equivalent resistance, we then have to take the reciprocal of that. We have to flip it upside down. So if we're increasing something and then take the reciprocal, the equivalent resistance actually decreases. So when we add this second resistor in, the Req decreases. And if the voltage, the battery voltage, stays the same, that means the current increases. Another way of thinking about that is saying a closed switch is like something with no resistance. So we took a resistor that was infinite resistance, an open switch, and we made it no resistance, closed switch. There's still resistance in this branch, but we took away the infinite resistor and put just essentially a resistor of nothing in there. That's going to decrease the equivalent resistance. I know I drew these as resistors, but if these were light bulbs, the one that always has current, that would be this one here, because they are on paths that create a complete circuit. The one that always has current would be lit up. The other one comes on when the switch is closed. And again, like I said before, a light bulb that burns out is kind of like an open switch, okay? I wouldn't say a light bulb that's on is like a closed switch, because a closed switch has no resistance, and a light bulb definitely does have some resistance to it, but light bulbs that burn out are like open switches. They stop the flow in their particular branch, or the whole circuit if that's how they're positioned. So there is a little bit about the junction rule, the loop rule, and any switches and burnouts. When you come back, we'll talk very briefly about power, and also very, very briefly about motors and efficiency, and then we'll be done with the notes, the video notes for the electricity unit.